good morning. This is a wrap up to the problem that I've been trying to solve, which is to do with a weak bar, which is too thin but very handy. When I put this weight on here, this bar is so light compared to the weight that it doesn't really matter. I don't have to include this in any of my calculations. I can ignore it. So I've gone for this bar, which is great for sliding the weights on and off, but unfortunately it's as heavy as a weight, and it is going to affect my calculations. So this is out of the way. The work we're trying to do is too demanding. This is out of the way, so I'm left with this. I know that was £5, and in the work I did yesterday I calculated this to be £6. But how can I be sure that my calculations are right? So I've got this little board of math here. The bar I calculated at £6. The weight is known to be £5. So the common factors, having some of the things that you learn in Saxon math are about common factors, and here we have two numbers that which go together. 6 times 5 gives me 30, 5 times 6 gives me 30. In other words, I can actually put these into a system of balance. In other words, if I take this £6 weight and put it 5 units from the fulcrum, I'll get a value of 30. If I take the £5 weight, and I've written this down wrong, if I put that 6 units away, the £5 6 units away, that'll give me a value of 30. So I'll have the weight here and the bar there. Now, initially I was thinking about trying to balance a bar on a bar, and that was just giving me quite a few concerns. So what I've decided to do is I've taken a stud which is laying around, which is a piece of wood. I've put that into balance, so I made it balance, and then I'm going to add the flat weight because it's flat and it's easier to put on first, and then the bar, and I'm going to put some little sticks either side, some lightweight sticks, just little wedges so it doesn't roll off, and I'm going to see if I can't prove that the bar actually weighs £6 by using this formula. 6 times 5 equals 5 times 6. So I'll just put that there. That's the plan. So I'm going to come on over, and here we have it. There is the wood, and it's in balance. I've got these little wedges which I'm going to be using, and on here I've marked the unit 5 inches apart. So I'm going to just call this is 5, 10, 15, 20. I'm just going to go 1, 2, 3, 4, 5. Over this side, 5, 10, 15, 20. I'm just going to go 1, 2, 3, 4, 5. The system doesn't care whether you count in inches, centimetres, metres. It only cares if it's in equilibrium. It's just very sensitive to something else. It's called gravity. It's very sensitive to gravity. The gravity is out, it's going to seesaw. Where the gravity is in balance, it's just going to stay as it is. So there's the bar. That's still going to be the hardest to put on. This is the £5 weight. According to the math, we said we're going to put this at 6 units away. 1, 2, 3, 4, 5, 6. That goes there. Now this is going to be easier to slide around and adjust. This is going to go 1, 2, 3, 4, 5. 5 times 6 is 30. I was going to find the centre of balance point. It's going to be somewhere around there. So if I put this on, it's tilted now. So just going to push it down a little bit. And there we have it. Not quite right, so I just need to shift this up just a touch. Move that up here. As I said, rolling objects are much harder to work with than flat ones. I'm going to turn this around, maybe I'll get a better resistance from it. And also having a wingspan. Very close at that. So I've put the system into balance and it is balancing. So I've got a value of 30 on this side, distance times the weight, 1, 2, 3, 4, 5. 5 times 6 is 30, and I've got a known 5 pound weight over this side. 1, 2, 3, 4, 5, 6. 6 times 5 is 30. So I can be super confident that my bar here is 6 pounds in weight. That means that when I use it, I'm going to have to think about its centre of gravity. I'm going to have 6 pounds. Let's say I go from this end. 1, 2, 2.5. 2.5 times 6. I think we're talking about 15 pounds of extra force. So I'm going to upset the system. So when I put it onto my fulcrum, and I put it on like this, I immediately have, from this bar, 6 pound bar, pulling down 15 pounds of additional weight. So that means that I might only need 85 pounds when I start working on tyres. But that's just something to bear in mind. I really had to calculate that 15 pounds is very significant. I don't think this bar here constitutes 1 pound. Really lightweight, and as you can see, when I put this on, it just gave, and so I could ignore it. In all my calculations I could ignore it, but this bar is just too significant. 15 pounds, that could really throw out any calculations. But now we've got the value two ways. We've got the value through actually putting the system into equilibrium. If I recall what I did something like this. 18 inches, something like that. I put it there, and now I've just used this one where I found the centre of gravity on this flat stud. Put it there, and then I balanced it out. So this way it was all unknown. This way we had no idea what it was going to be. We had to do some calculation. I hope you enjoyed the math. I hope you enjoy the fact that math is very unlike spelling and language. With math, You can change things around. You can go backwards, you can go forwards. So I can set up a system using this bar and these units, or I can go back to the original, and the original here is I have this weight, this distance here, which I calculated the centre of gravity. That was 9 inches, 3/4 of a foot for you fraction lovers. And then I added together what this 1.5 times 5, so that's 3/2 again for you fraction lovers. And then the centre of gravity for this was right here, so that was 2 times this unknown amount. So I've got the unknown amount over here, which I've called y, and then I've got 3/4 times y over here. And then if you followed the math page, then I increased the values. I used my imagination. Well, let's say I multiplied it. Let's say I made the bar much longer. And with math you can do that type of imaginative exercise. And so I brought it all into equilibrium, and then moved the y's around, and I just ended up with the 5 over here, and it's this distance, the 1.5 times the 5, and then we figured out that this was £6. Then we've just proved it. We put this bar over here. We said 6 times 5 is going to be 30, and we said 5 times 6 is going to be 30, and we proved it again. So now we know exactly what value this has, and we also know exactly, because we know about centre of gravities, that 2.5 times the centre of gravity is probably going to be a little bit bigger, because I've got that at the end. But I'm quite happy to say this is, when I put it into leverage, I've got £15 of extra force coming at the job, and that allowed me to be make some good calculations. So thank you so much for joining these side videos. We're now going to get on and get the truck out into the sunshine, and we're going to do some lug nuts. We're going to talk to them. We're going to get the torque up. The poundage is about 100 pounds to hold it on. That's times 5, so that's 500 pounds of pressure to hold that wheel in place. Foot-pounds of pressure, and then we're going to knock some of those lugs off and just see if we can prove the maths out in the field so that we can make it safe. This is what I love about being outside. You just find all sorts of interesting creatures, and we have beautiful piece of life. It uses the numbers all the time to get around. It even flies when it wants to, and it doesn't have a number system, it just gets on and does it. But we're making buildings that want to stay up, we're making machines that we want to move and go fast. So we have to be aware of those numbers, because we're creating new purposes all the time. This little beetle here, it was born to fly. We weren't born to fly. So as a result, when we take to the air, we've really got to do some number crunching. Thank you.